Welcome everyone, and thank you for being here on late on a Thursday afternoon. I know we're between you and some awesomeness at the party tonight. Hopefully we can get excited about accelerated computing. And I suspect there's a few out here that have experience with FPGAs, probably not most of you. So you're interested in how they can accelerate applications, interested in the development process. We'll cover some of that. And I want to turn it over as quickly as I can to Peter and Rami to talk about specific application experiences or development experiences using F1 for their genomics applications. And they've got some pretty exciting story to tell about how powerful FPGAs can be at scale. But first I want to kind of set the stage and talk about acceleration in general, right? So when we think about accelerated computing, it can mean many different types of acceleration. Today, you're hearing, or this week, you're hearing a lot about GPUs, of course, today about FPGAs. And the real concept behind acceleration of compute, a good metaphor for this would be the business jet versus the Shinkansen, right? The idea behind acceleration is to take advantage of massive levels of parallelism to increase throughput. It's all about throughput, right? And the business jet's a great metaphor for a high-end CPU, right? It goes fast, right? It carries a limited number of passengers. It's very flexible. You can turn it, go anywhere. Unlike the Shinkansen, and the Shinkansen's all about throughput. It's all about running as many passengers down the line as you can in a given amount of time. It goes relatively fast, but not as fast as that business jet. More efficient in terms of fuel economy, right? A lot of good metaphors there for accelerated computing. So on AWS, there's really two types of accelerators today, GPUs and FPGAs. The P3 instances that we announced and launched recently, based on NVIDIA Volta V100, are outstanding for doing many types of high-performance computing problems, accelerating, for example, double precision floating point computations in finance and engineering and deep learning training. On the FPGA side, the F1, based on the Xilinx UltraScale Plus devices. That's what we'll be talking about at length today. But I really want to characterize how these are different, how they really serve different needs, different applications. Think about a GPU. A GPU is really a massively parallel set of compute cores, right? CUDA cores, as NVIDIA refers to them as. And these CUDA cores are really optimized around parallelizing operations. For example, originally shaders used in graphics, and then later things like financial calculations or engineering calculations, double precision floating point calculations that you can parallelize in an extreme way using the GPU. Most recently, deep learning training is an outstanding example of using GPUs to parallelize the problem. A GPU is really a massively many-core architecture, right, that has at its heart an instruction set. It has data paths that are fixed. It has an architecture that's fixed, right? But it's highly parallel. An FPGA, on the other hand, this allows you to craft whatever instructions you need with whatever data paths you need, whatever control functions you need. It's very flexible from an architecture perspective. It does not have an instruction set unless you create one for it. It doesn't have fixed data paths unless you create those yourself. So it's very flexible, but it does require more work to develop the applications. Another way to view this, perhaps schematically, right? Think of the CPU core. A modern processor core is going to have multiple CPU cores. Each of those CPU cores has multiple ALUs, right? Arithmetic logic units. It's going to have cache architecture. It's going to have various control functions in there. It's going to have various layers of memory controllers, but it's built to be general purpose. It's built to support operating systems, general purpose applications. GPU, next step over, also has compute cores that have instruction sets, that have a fixed architecture. There's just a lot more of them. And so the amount of, let's say, compute that's being performed for the number of transistors on the chip is much higher in the GPU than the CPU, but it's less general purpose. And then the FPGA, as I said, there's no instruction set. It's massively parallel. There's literally millions of programmable cells in there. They're connected by programmable interconnects. And you use different programming methods to program the FPGA because you have to place and route those logic cells. So very different and different applications that we can think about for them. So our goal with F1, with the F1 FPGA instances, is to make FPGAs dramatically easier to deploy, easier to develop for, really easier to use. Make FPGAs, if you will, a first-class citizen in the array of processing options you have, CPU, GPU, now FPGA, right? So they need to look and feel a lot like any other EC2 instance, but have FPGA accelerators. And we want to make sure that the development process is as easy as possible for application developers, in particular software developers, who are not necessarily savvy to hardware design level requirements, right? And lastly, we want to create the ability for those builders, those FPGA developers who have experience, to take their products to market to many, many other customers and other partners. And Edico Genome is a great example of that, as we'll see. So when you think about the F1 instance and how it differs from other EC2 instances, the most important concept to understand is this AFI, or AFI, the Amazon FPGA image. You're familiar already, of course, with the AMI, with the AMI, Amazon Machine Image, where you can bake an AMI or an AMI with an operating system, with applications. If you want to deliver that to other customers, you could use the marketplace. When you're using the FPGA instance, you also have to accompany that AMI with one or more AFIs that have the FPGA logic embedded within it. That AFI is provided to your customer or to your user in an encrypted and secure way. We provide those capabilities. We provide the ability to have a unique AFI ID, for example. You don't have to deliver your FPGA bit stream, if you will, to your end user. You can be secure in knowing that your work that has been implemented in the FPGA is secure. The FPGA itself is attached to your EC2 instance, the F1 instance, using a PCI Express interface, very similar to the P3 instance with the GPUs. It has local memory, DDR4, accompanying that FPGA on the accelerator card. So this allows you to do all kinds of applications in the FPGA that are memory intensive, that are compute intensive, and minimize the need to take round trips to the host, which is very important for the types of applications that are deployed on FPGAs. The F1 FPGA instance is available in two sizes, the 2x large and the 16x large. The 2x large has a single FPGA available to you, and you can see, of course, 8 vCPUs and a quite healthy amount of memory, some local NVMe storage. On the host side, it's really a very powerful EC2 instance. And then, of course, with the FPGA acceleration, it's extremely powerful for certain classes of applications. And then the 16x large expands that, of course, by providing 8 FPGAs and correspondingly more vCPUs and RAM on the server side. An important concept in developing for the F1 FPGA is the development tools. And the development tools for programming an FPGA are somewhat different from programming applications or developing applications for CPU and GPU-based applications. It's important to think about FPGA development as being a kind of a cross-compile environment, right? Where you're going to use maybe a non-FPGA instance type, like a M4, M5, C4, C5, as your development instance. And you can choose the size of instance that's appropriate for the design problem you have. On that standard EC2 instance, you'll deploy the FPGA development tools that are provided to you in the AWS marketplace. And these are tools that are provided by Xilinx to allow you to develop the application, simulate the application in software, synthesize and place and route the application, which is a requirement for the FPGA, generate the design checkpoint, as we call it, that gets ingested to create that AFI. All of that can be done on a standard EC2 instance. And as I said, you can choose an EC2 instance of the size that's appropriate for the phase of the design that you're in. For example, if you're just doing initial simulation and development, you could choose a smaller, less expensive EC2 instance. When you're ready to do place and route and do the more memory-intensive parts of that flow, you could choose a larger EC2 instance. And importantly as well, if you want to parallelize that problem, in many cases, for example, you might want to do multiple synthesis and place and routes with different parameters to get the best possible performance, you can parallelize that as well using standard EC2 instances. When you have then the result of that, which is the AFI, the OFI, and you're ready to deploy on the FPGA, then you'll launch the F1. You'll deploy your application via an AMI into the F1 instance itself, and the OFI will be loaded via software. And we'll go through those steps in a little more detail in just a moment. Developing for the F1 instance requires that you use an SDK for the software side of the application that's running on your host, on the CPU, and a HDK, a hardware development kit, that's used for the development of the logic in the FPGA. It's an important distinction here. If you're using hardware-level design tools, the HDK provides all of the libraries you need to integrate with the Xilinx development tool flow. If you're using a more of a software development flow that we'll talk about in a moment using OpenCL, the HDK provides you those higher-level OpenCL APIs from the software side and from the hardware side. When you're developing your FPGA logic, you're developing what we call the custom logic that goes into the FPGA. That custom logic, for example, to do maybe a video processing pipeline or a genomics pipeline, some accelerated analytics application, for example, that application that you develop will be connected to the software side via the HDK and what we call the FPGA shell that abstracts the I/O to connect to the software side. And we provide you with the necessary APIs, necessary hardware interfaces so that you can easily connect those things together. And that's important because if you've done any hardware design in the past, any FPGA design, you'll know that designing the I/O can be just as difficult as designing the logic itself in the application. So we help you abstract, take care of that I/O, and just make it much, much easier. So to summarize these steps again, you'll use the F1 developer AMI, right, that includes the Xilinx tools and other tooling that you need and libraries to develop the application, to create the custom logic that will go into that FPGA. You'll generate from that using a design checkpoint, as it's called. That will be combined through a process that we provide on AWS. The DCP is combined with our shell to create that OFI, that AFI. That AFI is not something that you will ever have, will ever deliver to you. You get an ID to it, so you can access it and request that it be loaded into the FPGA. So it's a very secure environment, encrypted environment, allowing you as an application developer to secure your application that's running in the FPGA. From the software side, you can load and unload different AFIs in your application if you desire, or you can just have a single AFI that's delivered with your AMI for the complete application. And you can deliver that via Marketplace to other customers. OpenCL is an important innovation in the FPGA world. And this has been embraced by Xilinx, it's been provided in the Xilinx tools. We provide it in the Amazon developer, or in the F1 developer AMI. OpenCL makes it much easier for software programmers to develop custom logic and the I/O interfaces for FPGA accelerated applications. So it makes it possible for you to use C and C++, to use much easier and more comprehensive software development methods to describe and optimize and implement your application. Really does abstract away many of the underlying details of the FPGA and of that design process. So OpenCL is available now. We include a number of examples. We have tutorials online that I can reference in a few moments, helping you to understand how to program accelerated applications using OpenCL. I do want to say, though, if you're using if you're developing applications using either hardware design methods or using OpenCL, it is important that you have some knowledge of the underlying architecture, that you understand the basics of FPGAs and how logic is parallelized and pipelined and loops are unrolled so that you can get the best possible optimizations out of your applications. But OpenCL provides you with an alternative path. Rather than using hardware-level interfaces, you can take a path into the FPGA development using C and C++ entirely through the path. But other than that, the flow is very much the same. You'll generate the custom logic using OpenCL. That will be ingested into our tools. The result will be an OFI, an AFI, and that OFI can be loaded onto the FPGA when the application is launched. And that marketplace integration is extremely important for developers. If you have custom solutions, if you have expertise in FPGA design, it's really quite easy and quick to get started with F1 to, for example, take an existing application that runs in physical hardware and migrate that to AWS. And we'll hear the story again from Edico Genome about how they've done exactly this. They've taken a hardware-based product for genomics processing. They've migrated that to the cloud. And so now they have two options. They have the option of offering a physical application for their customers or a cloud-based application, following the customers wherever they're being deployed. So again, to summarize, you'll take your Amazon machine image, combine it with the OFI, create the complete application, and deliver that via Marketplace to the customers. Let's talk now about use cases for FPGAs. I described earlier the fundamental differences between CPUs, GPUs, FPGAs, and one of the things I described is that an FPGA doesn't have an instruction set. It allows you to create arbitrary bit widths, for example, and there are many applications in which that kind of flexibility is extremely beneficial, and some of them are listed here. In financial computing, there are certain use cases, for example, using extended precision arithmetic or doing Monte Carlo simulations on random numbers. The financial community is also very experienced at using FPGAs, for example, high-frequency trading. So there's a lot of use of FPGAs already in the financial sector. If you look at genomics, we'll hear about that in a moment. It's almost a perfect use case for FPGA acceleration because you can get away with very few bits in processing genomics data and doing comparisons, for example, of two sequences of DNA. And the image and video processing, that's long been served by FPGAs. Physical devices that you might buy from suppliers of broadcast equipment, for example, are chock full of FPGAs to do that streaming video at various bit rates and bit widths and so forth. Transcoding devices, for example, or devices that do image stitching and dewarping and so forth. Big data and machine learning is interesting, and one of our partners, Rift, does quite a lot in this space, doing processing that's somewhat akin to genomics processing, but doing it on text, for example, analyzing very large amounts of data with things like distance calculations. Test and measurement, there's a lot of use of FPGAs already in edge devices. And so organizations such as Natural Instruments that have devices that are out in factories and in smart sensors and so forth can use FPGA processing both at the edge but also conceivably in the cloud to do a lot of that filtering, triggering, and so forth from these devices. And the security, data security, cryptography, data compression, and so forth, many good successes for many years in those spaces using FPGAs at scale. And then also in the developers, in the marketplace, you'll find developers of tools, right? So there are next generation compilers, there are libraries, there are all kinds of tools in existence already for FPGAs that are finding their way now to cloud. Great examples of this, Reconfigured.io. In Reconfigured.io that provides a Go language compiler for FPGAs, a great alternative to using C and C++. Falcon Computing, another one, providing compiler technologies, next generation C compilers for FPGAs. So you'll see more of these over time. both existing tools for FPGA design, for example, simulators and advanced synthesis tools, as well as next generation compilers and libraries. Oh, there we go. Again, I want to emphasize this marketplace. It's so, so important. Many of the end customers, potential end customers of FPGA acceleration, from large enterprises to startups who are doing perhaps interesting things with large amounts of data, whether it's image processing or whether it's text processing, don't really know how to get to the FPGA accelerated reality that they could be in the future. And so it's very important that we have a rich ecosystem of partners providing complete solutions for accelerated applications such as Edico Genome, or perhaps components of larger solutions. A good example of that would be NG Codec in the video codec space, who are finding themselves on marketplace, offering their services and their IP, their applications to other consumers, whether they're other partners or end customers. So the marketplace is very, very important. And for existing FPGA developers, and there are literally thousands of them out there today, it provides an entirely new channel, a new way to get their FPGA accelerated solutions into a much, much larger selection of end customers, right, serving their needs. So it's very important for the advance of FPGA computing that we offer this marketplace, and it's very well supported with F1. So to get started with F1, we have tutorials available online. We have the SDK and the HDK available on GitHub. There was a workshop earlier today, and I think some of the materials from that will be available. I put a link in here. Don't try to just write it down. But if you go to the AWS Labs GitHub site, you can find the FPGA development environment, in particular the HDK and SDK and the documentation and the tutorial that I'm showing here that'll help you step by step to understand that development process. This particular tutorial walks you through the creation of an FFmpeg application and the accelerated IDCT component that's an important part of that. Shows you how to use OpenCL to create that kind of application or migrate that kind of application into the F1 FPGA. So with that, I'd like to cede some of my time and turn it over to the Edico Genome team to talk about their experiences migrating an existing application in the genomic space to the F1 FPGA. So Peter.
Thank you very much, David, and thank you all for being here. I know it's one of the last sessions, so we'll accelerate your access to the party tonight. So let me just give you a quick overview of our company, Edico Genome. We're about 5 years old now, but what's really important, as Dave pointed out, we have developed accelerated genomic applications, and those applications are centered around running on FPGAs. So now the question is, why is genomics a good application to be deployed on F1 instances and FPGAs in general? Well, so you can see that we've recently had a world record for the fastest genetic processing and diagnosis. We've been participating in 2 Guinness Book of World Records, the most recent one with AWS and one of our partners, Children's Hospital of Philadelphia. We've analyzed 1,000 genomes, which is roughly 100 terabytes of data in about 2.5 hours. And what's more important than that impressive number of the amounts of data that was processed is also the cost point at which that can be analyzed. So you can do the math yourself. A F2 instance is about $1.65 times 1,000 times the number of genomes. So, or the time that it takes 2.5 hours. So it's unprecedented to have that kind of processing in that amount of time and at that cost point. So that's one of the very good examples of why it's important to have processing on FPGAs and to use the bullet train that David mentioned as opposed to a jet. What's very important about genomics as well, it's growing fast. You know, all the diagnosis for cancer will in the future be centered around genomics. Precision medicine that you might have heard of, all the drugs currently that's being prescribed is only effective on a relatively small number of people, and you always get the issue where if you get prescribed medication, you have to go from, you know, try different kinds of drugs until you find something that's effective for you. And genomics is sort of underpinning all of those kinds of new technologies that's coming in healthcare. So what that means is that you need better kinds of processing for all the people that needs to be, of all the data that needs to be analyzed to have to facilitate all these medical applications. One person's genome is about 200 gigabytes, so it's a lot of data. And, you know, the end of Moore's law, the flattening off of Moore's law is really a very important catalyst for doing things on more efficient processing platforms like FPGAs. Our value proposition is clearly we can do things a lot faster that I've talked about. The cost as a function of the speed comes down significantly. And of course, the flexibility and the scalability that an F1 kind of application or platform allows for this kind of technology. So in addition to these three components, we also have developed pipelines for different genomic applications that have unprecedented accuracy. And again, that's part of the advantage of being able to do that on F1 or FPGA instances, because you don't have to take shortcuts. You can develop really complicated algorithms and deploy them on these FPGAs and still get all the previous advantages, which is the speed, the scalability, and the cost. So, you know, very applicable to have F1 instances in the cloud and to have FPGAs available to everybody that want to develop applications. So our DRAGEN, that's our name for our pipelines that we've developed. On AWS Marketplace, we have a wide range of those. We have applications for Germline, which is sort of your, where you can see your inherited diseases and predispositions. Somatic, which is cancer-based, RNA, population scale processing pipelines. So we have a wide range of applications that's running on these instances and that's being accelerated. So, but you might all wonder how all these algorithms work and what the architecture is. And I will give it over to Rami Mejia, who is our VP of Engineering, that will give you a little bit of a geeked out feel for what all of this means. Thank you.
Thank you. Hi, my name is Rami. I head the engineering at Edico, so I'm gonna explain a little bit how we accelerate genomics in general and what's our strategy. In general, what I've displayed here on the screen on the left is what the CPU does in our genomics application. What it really does, it takes the genome and chops it into pieces that different CPU cores can attack independently, right? So that gives you parallelism and gives you speed just by running on more CPUs. And that's something you can do in instances that are not specifically F1 with no FPGA. Then the next part is related to the FPGA. So when each one of these threads that's trying to analyze a part of the genome encounters an operation that's very costly from a CPU perspective, it sends it over the PCIe bus of the server to this FPGA chip. And in this FPGA chip, we have basically made an architecture where we can load different accelerators that can accelerate different pieces of the genomics algorithms. So when each one of these threads finds a need to accelerate something, it sends it here, and if the accelerator is present, it will compute it very quickly, send it back, and the software can continue on running. And this way you offload most of the work to the FPGA. Having said that, we also have the ability to reload these accelerators on the fly during each run. So typically, a genomics algorithm will basically do a map align phase, and in which we load all these with map align engines and perhaps a decompression engine for decompression and a compression engine. And we basically do all the work. When the data comes back, then we start the second phase, which is the variant calling, and we swap again now to new accelerators that are specific to variant calling, such as hidden Markov model, Smith-Waterman, reference-based compression, CRAM, and others. So we have a whole library of those, and we keep swapping them in and out based on the part of the algorithm we're running. Okay, so as Peter mentioned, we started from an on-site solution where we developed all these algorithms on our own board, on FPGA, and the opportunity to port onto F1 on AWS came, and so we had to architect our software and hardware in a way that every time we develop a new algorithm, we don't have to make two different softwares one for the on-site, one for the cloud. And there are new boards that we're selling on-site, so we want to have an architecture that basically decouples us from the underlying hardware. And that's what we come up with. So this is the layer that basically has all the genomic accelerators, including the compression and decompression. And here, this is the hardware layer that will basically allow you to talk to the memory available on the board. And depending on which board we're using, we'll be using a different component here. And there's a crossbar that allows you to talk. So essentially, our IP on AWS lives here. And the on-site, it lives here, but also we have that implementation as well. On the software side, we would like to have all algorithms be exactly the same on-site, on the cloud, or different boards, versions, and what have you. So the pipeline layer is really not affected by any of this. The hardware abstraction is, there's a hardware abstraction layer that basically hides you from which board you're using. And there's a DMA driver that talks to this hardware abstraction layer to the board, and it sends essentially packets back and forth. And the I/O layer allows you to, for example, read from S3 or from NFS for the data access. So this summarizes what I mentioned. So the size of the FPGA, to note, is on the cloud is really big, and we are able to take advantage of multiple FPGAs. We elected to use our own DMA software driver initially to basically speed up our development. As I mentioned, the software hardware abstraction layer insulates us from the platform being different clouds or on-site versus cloud. Okay, so in terms of what we are able to do in terms of speed, so our acceleration is over the best algorithms available, the ones that are already optimized in C. If you take the same amount of CPU cores, is about 43 times or 40 times. And if you talk over Java code, which is often what's used in the genomic space, is about 100 times acceleration. And you get different accelerations, whether you use the F12X and F116X. The A16X has many more vCPUs and more FPGAs, and we try to take advantage of both set of resources when we're running the algorithms. Okay, so this is an interesting part of the port that we did to the cloud. So we've ported to the cloud. We used this abstraction layer. We were able to move to F1. And once we were done with that, we really achieved this piece here, which is once the data is on the instance, we can run very fast. Then we realized that actually to take full advantage of the speed, we should basically also cut down these other pieces. These other pieces here are related to downloading the data from S3 to the instance. And we have two sets of data we download. We download a reference and the actual input files. And we produce outputs that we send back to S3. So of course, on an on-site system, the reference is usually always present in the same place, so we don't have to download it. And the file is also accessible through NFS. You don't have to really download it. So we went ahead and we analyzed the time. And as you see, since our acceleration is very good in this part, these pieces here of upload and download are pretty big compared to the rest. If you were doing a BWA GATK in Java, this would be really 5% of your run. But here it's pretty dominant. It's taking as much time as the processing environments. So the first thing we've done is we stream from S3. So really, we don't download the file. We open the file, and we do multi-part download on the fly and feed it to the software immediately. Of course, the reference has to still be downloaded because without the reference, you can't start the processing. So we shortened the cycle a little bit, but we still had this reference to download. So after that, we basically figured out that we can compress the reference. So on the on-site case, this was not necessary. We compress the reference, download it, and decompress it before the analysis. So that cuts down all this time. And we implemented upload streaming. So with that now, we really are dominated by the execution time of the instance. And any optimization we do here benefits us directly. This is especially important if your files are small, an exome, for example, or a panel, because otherwise you're dominated by a reference download that's very big. So this allows you to be very efficient. And of course, the last step is to shrink this part here by using a 16x instance instead of a 2x if you elect, or with each software release that we do, we optimize and we move more things to the FPGA, and we're able to shrink the time. Okay. So when we basically develop all these algorithms, of course, there's the architecture and how to speed up things. But really, to a customer, what's very important is that you have not a fast algorithm only. The priority should be always the accuracy. These are algorithms used for detecting diseases and treatments. So the priority is accuracy. So we have our first release of our algorithms was called a suite called V1. And we just released today V2, which is much more accurate and offers many more pipelines. And I'll show the results of that in a second. So these curves show the accuracy of a SNP detection and indel detection versus an algorithm such as BWA GATK. And with DRAGEN V2 that we released today on AWS, you could see that we are able to detect 1,000 more indels and significantly more SNPs. And that's pretty significant. And we use this algorithm in a PrecisionFDA challenge recently, and allows us to do very, very well. And I'll cover that in a second. The somatic case, I use one example of a somatic case, and you see here in the indel case, the gains are even more significant. To touch also on what Peter said earlier, a lot of these algorithms before the FPGA acceleration were very difficult to consider. If you'd consider them and put them in software, it would take so long to execute that we would be reluctant to implement. With the FPGA being there, we go for the most optimal algorithm and go figure out how to optimize it later on. DRAGEN V3 is an iteration of the new iteration that will be coming up beginning of the year. And in that case, we focus on the SNPs. The previous slides focused on the indels for the V2. The V3 gives you a significant gain in the SNPs and much less false positives. So this is the last challenge of PrecisionFDA where we participated. The objective of the challenge was to find 50 hidden variants in an exome. And of course, if you find them, you could also measure yourself for your accuracy against the rest. So the hidden variants are meant to deter anybody from cheating. So if basically you don't know them, so there's no way you can guess. So among the people who found all the 50 variants, we ranked first in indel precision, recall, F-score, and SNP F-score recall, and we ranked second in SNP. And the slide I showed before is V3, where we will address the second place problem that we had. All right, so we talked about accelerating an algorithm onto F1 or an FPGA. We talked about how we make the platform, the software platform independent. We talked about how to make the algorithm fast, but you know, there are use cases where, many use cases where people need to scale and basically analyze 1,000 genomes. Such a case, or 20,000 genomes. Such a case is somebody analyzed a bunch of genomes in the past. They'd like to move to a new reference, and they want to basically get all the data onto the same reference, so they need to rerun with a new reference. So with AWS team and CHOP, Children's Hospital of Philadelphia, we leverage the AWS services, mainly AWS batch. Of course, the F1 instances, we used S3, we used ECS, all of those, along with our workflow management system, which is our own database that tracks progress of the genomic pipelines. We were able to run 1,000 instances in parallel, and we processed actually 1,020 genomes. And the total runtime was about 2 hours 25. That includes upload and download, so the real runtime was 1 hour 57, I think. And it was dominated by one sample that was at 45x coverage. So, you know, depending on samples, if they have a lot of coverage, it'll take longer. So that's the scalability. So AWS batch plus F1 instances is really a potent way to scale genomic analysis. In terms of if somebody wants to deploy these instances globally, this would be a reference architecture for that. The architecture basically allows you to have the smarts in the US East, and the compute nodes today are present in US East, US West, and EU West. So we have tested actually the ability to do that. This is a small summary on the word reckon run of the 1,000 genomes. And these are the statistics. You see that the coverage was, on average, 40x, and the analysis max was about an hour 55. But the mean is actually quite smaller. So in summary, the FPGA acceleration results in up to 43x improvement for genomics application. This is really if you're comparing to the best C++ that we know about. Very important if you can take advantage of streaming from S3 directly. It cuts down on all the download time you need. Parallelizing across FPGAs on 16x gives us a lot of acceleration, extra above and beyond the 2x. The per second billing and spot instances are very, very important. On 16x, if a run takes 20 minutes for a whole genome, in the past you used to have to pay 3 times the amount of time, even though you're only using it for 20 minutes. And now you really can go for the fastest instance without worrying about the rollover to the hour. Spot instances on F1 to X, of course, the price depends, but we use them extensively, and we're able to often get these instances between 25 cents and 40 cents. And the marketplace allows us to release our software quite often for people to try it. We have partners that resell our solutions, such as DNA Nexus and BaseSpace, but the marketplace is a way for people to try them on their own if they wish to do that. Thank you.
Thank you, Rami. So I really, really like that example. And if you think about the previous state, right, the previous state of Edico Genome, having to develop a physical application in a box that would be deployed at some research hospital, for example, or at a cancer center, and not at scale, right? It becomes a bottleneck. Even though it's accelerated, it's still a bottleneck. But then once moving to cloud, the ability to scale in a very short period of time to 1,000 FPGAs to accelerate, in this case, pediatric genome processing, which is highly impactful for human health, is just super exciting. And that's exactly how we should think about acceleration in the cloud. We can accelerate the individual tasks using GPUs and FPGAs, and then we can continue to accelerate using scale out, as was very well demonstrated with 1,000 genome run. So super exciting, and thank you very much for sharing that. We have time, about 10 minutes left for questions, and we can go over too. If you have additional questions about the development process or about the path to market, we're here. And there's a microphone over there if you'd like to ask any questions, or we'll stay here for questions one-on-one. Yes, please.
Do you see these currently or potentially in the future being used for mining digital currencies?
It's an excellent use case for FPGAs in terms of the characteristics of the algorithms. I would suggest you give it a try, run them on spot, and see how you do. Yeah, crypto applications in general are a good fit for FPGAs, absolutely. Other questions? All right, so we'll be here for the next 10 minutes. We'll take additional questions if you have them. Again, if you want to get started, go to that GitHub repository that I mentioned earlier. Go through the tutorial. You can really, literally, with lunch money, launch an F1 instance, go through that entire tutorial, use the development environment, and see how this all works. So thank you very much for coming today.
Thank you.